This episode with Dr. Reinhard Genzel is one that you don't want to miss. He's a very, very open, vulnerable, honest, and hilarious individual who was destined, perhaps, if he didn't get more into physics, to become a great athlete and even participate in the German Olympic team in the 1960s. So he would have won a golden medallion, perhaps, no matter what he did in life. But today we're talking primarily about his work in astrophysics that garnered him, along with Andrea Ghez, my colleague up at UCLA, who I still hope to get on the Into the Impossible podcast. Please, if you are listening out there, Andrea, I'd love to have you on. But we also get into the importance of mentorship, of how he learned from really two men in his life, two father figures. One, his actual father, Ludvig, who's a great physicist himself. You'll hear him touchingly and lovingly talk about his late father. And also his ideological father, Charlie Townes, Nobel laureate from UC Berkeley, who really inspired this quest to look in the infrared to peer through the dust that conceals and constrains our vision of the inner workings of the Milky Way galaxy. He's going to hear about that. Where do we go from here? What can we do with this technology? And what he's most excited about. So now, sit back. Come along on a ride into the impossible with Professor Reinhard Genzel and yours truly, Brian Keating.
Any sufficiently advanced technology is indistinguishable from magic.
Open the pod bay doors, Hal.
Welcome, everybody, to another edition of the Into the Impossible podcast. I am your fearful host, Dr. Brian Keating, and we have had a segment on this podcast for a long time now called Nobel Minds, where we have featured to date 9 Nobel laureates in physics. Still trying to get some other disciplines, Reinhard, but so far they've all been too busy. Those economists, they get very busy. But Reinhard is a legendary experimental and astrophysicist. He's the co-director of the Max Planck Institute for Extraterrestrial Physics, professor at LMU, emeritus professor at UC Berkeley, from here, and he was awarded the 2020 Nobel Prize in Physics along with Andrea Ghez and Sir Roger Penrose. Andrea has yet to answer my emails to come on the show. I'm hoping she will. But Roger was on 3 or 4 times just last year, and you and I celebrated along with the world Sir Roger's 90th birthday not too long ago. And I thought it would be a great opportunity to introduce the world to the astrophysics that you do with your collaboration. And then we could have a discussion about black holes and how mysterious and wonderful they are and where the future of this field is going to go. So first of all, Reinhard, thank you so much for joining us on the podcast.
Glad to.
So I thought maybe you could show your slides that you showed at Sir Roger's 90th birthday party just a few weeks back in August 2021. Sir Roger is now 3 billion seconds old, but he doesn't look a day over 2,999,000,000.
He's an amazing person. Amazing.
He really is, and he's been a great friend and indulged me in some of my questions about singularities, extremal black holes, and other things I hope to get into with you. So, Ryan,
Brian. Of course, I mean, we might come to this later, but this. The weirdness of black holes, of course, often leads to interesting questions from the audience. And, one of the more common ones, of course, has to do with wormholes.
Yeah.
And I never knew what really I could say about this because, it's a speculation, but, how would you test it in reality? So I asked Roger, I said, Roger, I'm being accosted by these questions. And, you're an authority in this, tell me, what do you think about wormholes? And he says, oh, rubbish.
I remembered that we met each other in 2005 at the 90th birthday party for Charlie Townes, who was your advisor. And I later want to talk about recollections of Charlie Townes. I know he was a titanic influence in your life, and really... The path to the Nobel Prize really goes in large part, alongside him with your work. Sure. So if you would take us on your 40-year journey, that will take us back to where this all began. So, please.
Basically, there's sort of like a Russian doll situation here. In the innermost part, there is the research which I'm associated with in my group and the institute, and of course, in the US, Andrea Ghez and her group. And that's sort of the inner part of the Russian doll. The next layer, of course, is the more general question of whether these objects which general relativity predicts to exist, black holes, whether they really are there. And so then what we are doing is just one version of possible approaches, which in fact people have made, and surprisingly so, lately with great success actually, to test whether this black hole paradigm, as we call it, whether that's correct. The next level of the doll has to do with the universe as a more global entity, and the fact, okay, if you had such things as black holes, what is their role? Who ordered them, so to speak, and are they just there, and what's their role? And so that is an extremely surprising story, which also has been, we have been making empirical progress on this. Then comes the next layer of the doll, which has to do with general relativity. Here's a theory which is to start with associated with extremely famous theoreticians, Albert Einstein to start with, but then others, of course, as well. Schwarzschild, Kerr, Penrose, etc. And so the question then is this theory correct? And then most theorists, but maybe also some of the experimentalists, would say likely not. and that is sort of surprising. Here's one of the theories which, at least on the largest scales we know, namely that of the universe, rules supreme. And it rules also apparently supreme on the smaller scales inside the cores of black holes, where there supposedly is an infinitely dense thing called the singularity, which most of us, of course, feel, okay, something is missing in the theory, which is the expansion, the extension to the smaller scales as a quantum theory, and that is obviously missing. So this is really amazing that, on the one hand, that theory is now 105 years old. It was presented by Einstein in Berlin 105 years ago, and we're still working on it. So in fact, the experimental studies are just getting going. If you look into the future, it's very clear where I would put my eggs. Okay, gravitational waves. That's clearly the ultimate way, probably, of approaching these things so close as to then perhaps see some deviations from general relativity.
So I think the interesting aspect of the black holes is how much they captivate the mind and the intellect of not only professional scientists like us, but the mysteries that they reveal and provoke in the general public. And we've had on many guests, from Lenny Susskind, obviously Sir Roger, Delilah Gates, and the one thing that keeps coming back is that these objects are laboratories. And in some sense, I was a little bit surprised when the committee awarded you and Andrea, the prize. They didn't say black hole, right?
They did.
Yeah. So what is that? What was the reason for that choice of words?
That's. I would say I fully agree with that. They had to, because, and I think that the Nobel Committee is, I would say, generally very good about this. Remember the prize for Riccardo Giacconi was 2002 or 1. He could have gotten it for the detection of stellar black holes, and yet they didn't. In the citation, they wouldn't say it in this way, and the reason is that, of course, what we have not yet shown, really, none of the observations has shown, is that the so-called Kerr metric, which is describing the in theory, which is describing what we would call these objects without charge, and which have two numbers associated with them according to the theory, a mass and a spin, and that is it.
Yeah.
Okay, so that's the remarkable thing, that these objects are, extremely simple theoretically. There's only two numbers. So that means the theory says there are no hills, there are no valleys, there are no,
There's no hair. There's no hair.
and therefore there's no hair. That's right. And so this test of no hair, namely in mathematical terms, that all other properties of the object in terms of higher moments of mass distribution can be predicted by these two numbers, that is missing. Okay, that is missing both from the existing work on the supermassive black hole in the galactic center, and it is missing, in fact, also for the in-spiral of stellar black holes with LIGO. And so that's why, one has to be really careful and say, well, we have everything we've shown, everything LIGO has shown is that there are objects which, look like black holes and probably are black holes, but we are still not there.
It seems unprovable to say, because how else, what other evidence could one gather? Not for the singularity, we'll get to that later, but for the properties that, the Event Horizon Telescope has shown, that LIGO has shown, that you, Andrea, and your group has shown. What else do we need before?
Well, okay, that's a very good question, Brian. I mean, I think the answer most people would say is the no-hair theorem, indeed, and so for the gravitational waves, what would have to be done is the following: if you think of a black hole as really sort of an entity, and you bang at it. It starts to oscillate, okay? And so there is a characteristic, what one calls a quasi-normal frequency about it, which is essentially the time light takes to move around the black hole on the innermost stable orbit for the light. That's called a photon orbit. And so if you suppose you know the mass of the black hole exceedingly well, and then you had a piece of light going around this innermost stable orbit, and it would exactly follow that orbital time scale. Then you have proven, and you knew, of course, the spin, I should say. You know the mass and the spin, and now you make that measurement of this orbital time scale of the photons. Then you really have proven the no-hair theorem, or one version of it. And indeed, that's exactly what, in principle, the gravitational wave community would like to do. Why haven't they done it? Well, because the objects which they have looked at so far, namely stellar black holes, have a very short time scale of 100 milliseconds and less for this time. And there is not much time to build up signal-noise ratios. So it's just a practical thing. The objects are small, the time scales are short, and in fact, because they are small, the signal are really weak, although they are actually, and the objects are not that far away. So the ultimate object, everyone knows, is a massive black hole, and a stellar black hole which inspirals into it. For that, you cannot do that on the ground because of the frequencies of the orbital inspiral is much too long, initially at least. But because it's long, you can make very exceedingly precise measurements. So the space mission we all hope to have in space in about 15, 20 years might do that. Okay, so then we could do it. Another way of doing it is in the galactic center is to measure the spin. We're trying to do this with stars which are still further in than the ones which we had seen previously. If you're lucky, we will see such a star. And then if the radio astronomers could measure the size of the photon orbit, so to speak, it's called the shadow of the black hole, we know the mass exceedingly well, then we have a test of the no-hair theorem as well. So I think there's good hope that this will actually come about. But then, as you say, this does not solve the quantum problem of the whole thing. Quantum problem number one is we will not be able to send one of us with a rocket into the center of a black hole and check out the singularity, and then say, hey, it's actually not the Planck length, it's 2 times the Planck length or something like this, because we cannot send out any information, right? I mean, so that's a real problem. The other problem is the so-called information paradox, which is basically, as far as the classical theory is concerned, if you throw in rocks or refrigerators and a few cars and everything else into the black hole will all forget that. And so if you come back later and check it out, so to speak, you wouldn't know any evidence. But the quantum theory would tell you, no, absolutely not. The quantum numbers are stored somewhere. And there's even some proposals where they might be stored, namely exactly on the event horizon surface. And so then it might drift out like fumes, quantum fumes. And so if you want to speculate, that may be sort of the thing of the future. And of course, it could be that this will change the properties near the event horizon enough that it's measurable. It's extremely fascinating that it takes 100 years and we're still not done, right? I mean, this.
Yeah, and the more that we learn, the more mysterious these objects become. I talked with Lenny Susskind, who does have this proposal of the stretched horizon, as you just said, the kind of one, Planck length above what we would consider to be the event horizon. And I actually don't think it's a important distinction that, we say, oh, we can't observe these things in theory, even because the event horizon shields it. What I have an issue with is that people will talk about the need for quantum gravity based on the existence of an unobservable singularity, either in a black hole or at the origin of the universe, which I study. So these are two, as Roger and Stephen Hawking showed, unobservable, even in principle, regimes. And now that's not to say that they're right. It could be that that there was a collapsing epoch before the universe originated. As you probably know, your advisor Charlie Towns, when he won his Nobel Prize, his students Arno Penzias and Robert Wilson were busy measuring the CMB. And when they measured the CMB in 1964 and then released in 1965, their interpretation, well, I should say the interpretation of Jim Peebles and Robert Dickey and others, was that it was the after effect of a pre-collapsing phase to the universe, that we had witnessed the cycle. They never mentioned the Big Bang once in that paper. And I think a lot of people had trouble with that, the notion of Fred Hoyle and others. And I wonder, what do you make of these controversies in physics? The late, great Steven Weinberg, he just passed away. He used to say that physics thrives on crises, but luckily there aren't so many crises.
Well, I think, first of all, of course, this is the scientific principle, and that's what makes us indeed capable of telling truth from fake news, the famous fake news. And that is that we have a theory in this case, which is already pretty well tested in some regimes, and we keep going at it. Okay, I mean, but people are different. I think I've, even very good astrophysical theorists would tell me, say, a few years ago, before our latest breakthrough in a way, Reinhard, why are you doing this? I mean, everyone knows that general relativity is correct. Much more important is, so to speak, the cosmological evolution of the black hole. That is important because that affects galaxies and how they grow or not grow. But why do you trying to test general relativity? Well, because my physics side tells me, if we can't verify all the predictions of a theory, then the theory is in danger, so to speak. It could be wrong. Yeah. And we better check it out. And in this particular case, of course, by testing general relativity in the galactic center, we are also testing this paradigm that galactic nuclei, in fact, almost all galaxies we now think have such a beast in their midst, and in fact, it's a symbiotic relationship, right? So that they grew up together and and after a while, the black hole became active typically and started actually, damaging some of the galaxy they're embedded in.
When I think about the future of your field, and I definitely want you to show these wonderful images that you showed at Roger's birthday festschrift, as you might say. But before you do, the thought occurred to me that a lot of what we've learned in recent years, thanks to LIGO and other projects, was also what falls under what's known as multi-messenger astronomy, where you observe something in light, in electromagnetic waves, and in gravitational waves. Is there hope with the tools that you and your colleagues are developing that there could be a multi-messenger signal, say if one of these gas clouds, S2, whatever you guys call it, if one of those were to be gobbled up and you were to witness it with your AO technology, et cetera, on a massive telescope? And is there any hope that LIGO or some perturbation to the Milky Way's black hole, that could be a multi-messenger signal that would tell us something?
That's a very interesting question. I mean, the answer at first would have to be yes, but highly unlikely. Okay, why unlikely? Well, the situation is for moderately small black holes, the stars, if they come too close, do get disrupted, so to speak, and then outside of the event horizon, and then they fall into, partly at least, into the black hole. Part of it gets ejected. And actually, in the galactic center, there is some evidence we have that there is gas on an orbit which is almost straight in, if you like, which went into the central region and then came back out again on this orbit. But it's gas, not a star, or at least not only a star. And this gas cloud was extended. And so it's very, very much possible that is one of a case of one of a class of stars which from time to time do in fact come so close to the center of a galaxy that they would get disrupted. And at that time, of course, you would see gravitational waves. The problem is that this, statistically speaking, happens once every 30,000 years or so. So the chances of catching one of them, and that all in the galactic center, is really very low. In the more general sense, absolutely not. I think in a general sense, we are now in a time, as you well know, where people are looking for these transients, and they're finding them. And so if you then have a sensitive enough gravitational wave detector, you could look at these regions and then perhaps detect them. So chances are that this will be possible. Whether it's happening in the galactic center, there we really have to appeal to a lot of luck. This is sort of a very nice movie, which in fact Andrea made about 10 years ago, to just show the inner works here, if you like. So these are our test particles, our stars, which we've been looking at. And it's remarkable. Any theorist 20 years ago, when we discovered these, would have sworn that these stars cannot exist. Why? Well, we have a very good theory, of course, in principle, how these clusters around a black hole of stars should look like. And that is because the dominant thing is gravity, right? And so stars, if they're heavy, will over time move toward the center, that's correct, and get close to the black hole. But the time it takes are billions of years. These objects which we're seeing here in this movie all are less than, say, 50 million years old. Mm. So they couldn't have possibly, over time, by equilibrium processes, as we say, moved into the center. So the question is, therefore, how did they? And so they are a tremendous gift to us, because some of these stars, in fact, not few, this year we had another 3 stars coming in just like this famous star S2 did in 2002 and then again in 2018, and came as close as about 15 light hours. So that's sort of the, on the order of 100 times the distance between the sun and the Earth. So that's solar system scales.
Yeah.
Tremendous. Okay, tremendous. That gives us this ultimate way of testing it, because it does go so deep into the central region. But how, who did that? Who made these stars to go in there? And so that's one of these things in science and say in astronomy, certainly, that the universe has all these surprises for us. And sometimes the surprises are wonderful. Right? They really help the field to go forward enormously, because before we had this orbit of this particular star, we had sort of a statistical assessment of the situation. Not that it would be any different, but I mean, most physicists would have said, yeah, that sounds plausible that there is a mass in there, but a black hole, why? Could it not be a cluster of neutron stars or something else? And that's exactly, despite the fact that we had this breakthrough, why the Nobel Committee is still sort of a little cautious on this, because you could think, although not really anymore, that it's not a single black hole, for instance, but a double black hole. We think we have now actually excluded that also, at least to the extent that the second object is more massive than, say, 1,000 solar masses or so. Mm-hmm. But I mean, there's all of these things you have to check in, and that's check out, and so that's where time is needed, and that's where these journeys become pretty long-lived. But you're right. If you then get someone to help you, like gravitational waves, or very, very interesting for us would be this radio imaging, then you could make progress in a much shorter time scale. Okay.
Yeah, and when I think about the technology versus the theoretical technology, the hardware versus the software, so to speak, I think about LIGO. Obviously, tremendous technology, and it's purely relativistic in a sense. Event horizon, people quibble: are you really seeing the event horizon or just the light shadow? You already mentioned that. I think they're both fascinating, but still, you need numerical relativity. You need to treat it purely relativistically. And interferometry has been around for, 80, 90 years. It wasn't new technology in that sense. But I would say the technology that you employ, adaptive optics, laser guiding, et cetera, I think that might be interesting for my audience, because typically they're hearing about, well, this is a test of pure general relativity. But if I'm not mistaken, the fastest velocity of, say, S2 was about a few percent of the speed of light.
No, about 2.5%. Yeah.
So you wouldn't necessarily, you could do a lot with Kepler, just using Kepler, not Einstein. And so in a sense, the compact object or whatever as a test laboratory for general relativity, it's also a test for classical relativity, which makes it more interesting to me in a sense that the adaptive optics and the story of this 40-year journey, as you described it, where that begins, and how can we see through this? If you look up at the Milky Way, and I've been to the Southern Hemisphere, I've seen the Magellanic Cloud. You can't see, Sag A star with your naked eye. It's just impossible.
That's right.
So the Milky Way is rotten, filthy place with lots of dust, just like Los Angeles is. And I want to know, how can you see through the dust? How is this even possible that we could penetrate through this cloud that veils our vision and obscures everything?
Right. So that brings us back to the 70s, actually, and in fact, Charles Townes and his work in Berkeley, whom I then joined as a postdoc initially, and then as a faculty member in the early 80s. So the situation was that the so-called quasars had been discovered in the 1960s by the radio astronomers, looking just, what does the radio sky look like? And they found compact radio sources, pretty bright. And then they asked their optical colleagues, why don't you take a picture of those? And what do you see? And then they used Palomar, and they came back and said, well, they look like stars. Not very interesting, but so luminous. How could that be? And then the trick was that once you look at their spectra in the optical, you can see that they're actually highly redshifted in terms of their line emission, and therefore, if you interpret that redshift as an effect of the expanding universe, and you apply then the sort of the conversion from redshift into distance, then all of a sudden these objects, are billions of light years away, and so what looks like a little star actually is enormously luminous. So that went on in the 1960s, and people then start to think, what could create all of this energy? And turns out, if you would pack stars in that region, even if you work hard at it, it won't give you the kind of phenomena you would see, because by that time not only optical light had been seen in radio light, but also X-rays and gamma rays, your multi-messenger, as you see. And so it's clear these are unusual objects. They really have to, and so luminous, 1,000 to up to 100,000 times more luminous than the entire Milky Way. How can you have that? And that's where this crazy idea of black holes came in. Now, they weren't called black holes back then. They were called Schwarzschild throats. The strange word for nowadays. Schwarzschild throats. And so that is within a decade, people basically convinced themselves that the most efficient way to generate energy is to let material fall onto a big black hole. And before the material disappears behind the event horizon, that energy which is released can be leading to this enormous amount of radiation. So, next question, how do you test that? To test gravity, we know what we have to do. Think of the solar system, right? I mean, the solar system has our sun dominating the entire mass, and you have planets. And so if you go back to Tycho Brahe and Kepler, right, the way to do this right is you basically observe the motions of the planets. And then you use Kepler's laws or Newton, and then you find that if there is a dominant central mass and the planets are on orbits around that mass, well, then the innermost planets move faster than the outer ones by an absolutely predictable amount. And if you test that in the solar system, then you have, so to speak, proof that the sun dominates the mass by far. Well, so the same idea you would want to use also in quasars, but they're too far away. That was really very clear. They were too far away. And so then it was a critical paper by two British very famous theorists, Donald Lynden-Bell and Martin Rees, in 1971, who basically speculated at the time, well, maybe these black holes, which have been talked about now in these quasars, are not only present in these rare quasars, but maybe they're everywhere. Perhaps every galaxy has, and it's just that only a few are accreting material at such rates that they are bright and are called quasars. And in fact, that's our picture nowadays, not at that time. So what's the closest galaxy, therefore? Well, our own, by a huge factor. And so in the paper, in this 1971 paper, Lynden-Bell and Rees then actually made a sort of recipe of what should be done. It's not exactly how it didn't mention stars, and molecules were not known at the time, so they proposed more H1 observations, et cetera, and variability studies and so forth. But in the end, I mean, that's the idea. So let's go ahead and observe then the galactic center and observe all of this. And the answer, of course, is with the radio you can, but you can't get really close enough, at least not at that time. What about just looking at the stars and so forth? And that is impossible because of the dust in front of the galactic center, which attenuates optical light by so much. Even nowadays, you cannot practically observe the galactic center in what we would call the optical band. But if you go to slightly longer wavelengths by, say, a factor of a few, the extinction is so strongly dependent on wavelength that you can peer through the dust screen at a few micrometers, and certainly at 10 micrometers. And that's where Townes came in, because Townes, you see, he got his Nobel Prize for the invention of the laser and the maser. Was on the East Coast and many years and all of that. And then at some point, he decided to move west to California and start a new profession as an astronomer, okay? But he knew, of course, things which astronomers didn't know, which was, lasers, masers, and he knew about the possibly very exciting possibilities with infrared light. And infrared is exactly what you need. And so that he and his students then built a spectrometer and used that spectrometer to look at Doppler shifts of ionized gas in an infrared line near the galactic center. And sure enough, they saw that the motions of those gas clouds were very large. When I then joined, we did ever more of that. And so by the mid-'80s, we wrote a big Nature paper saying the galactic center has a few solar million solar mass black hole. So there it is, mid-'80s. So that's 40 years, 30 plus years ago. So it's clear that we thought we had the result, and Townes felt, okay, more or less, okay, we're done. But nobody else believed us, you see, and that's it.
How was that accomplished without adaptive optics? I mean, I know the story. I've had Claire Max in conversation before, and adaptive optics, I understand, was embargoed. It was a national security and et cetera. And we were
okay. So at this point in the 80s, 70s, 80s, we used infrared and long wavelength infrared, where adaptive optics actually doesn't really do much. 10 microns and plus we didn't have 10 meter class telescopes. Okay, so we would observe on 4 3 meter class telescopes at 10 microns, and there, if you have good seeing on Mauna Kea, you're doing okay. And the technique at that time, as I said, you measure the by spectroscopy, the Doppler motions, and so that is. But the reason people felt that they wouldn't believe us was exactly that. Namely, they said, well, clouds of gas are very tenuous things. Plus, it's ionized gas. Ionized gas, you can push around with magnetic fields. You can push it around with stellar winds. How do you know that this is what you're measuring is gravity? How do you know that this is orbiting gas? Could it be that it's actually ejected gas and so forth? And there's some truth to that. Although what we know now does show that we had the right interpretation, but the question is whether it's believable. So the big jump then came into the 90s. Step number one, exchange gas by stars, try to move the motions of the stars, and then make that measurement as precisely as you can. And precise in this case means you have to measure the centroid of a stellar object to more than 1/100 of its diameter due to the seeing or due to the resolution of your telescope. And that's where indeed it became clear you cannot do that with normal techniques. So that's where initially we used so-called spectral imaging, where you would take short exposures, and in any short exposure, in any short time, the atmosphere is, so to speak, then still more or less stationary. But after about thousands of a second, then the image gets distorted. And then two things happened at the end of that phase, which is number one, we all went to bigger telescopes. Andrea first in the mid-90s, we at the 2001, and then adaptive optics. Now you mentioned that already, that story of adaptive optics, actually like the detectors we were using. I mean, the imaging detectors in the infrared also had the same, if you like, heritage like adaptive optics, namely that for a long time, not now anymore, but at that time, they were all products of military developments in the United States because, of course, the military people wanted to look at Russian rockets and satellites and so forth. And that was their way of, look in the infrared, of course, you can look at the hot exhaust of rockets as they get launched. And that's the way to predict, so to speak, okay, there's an attack coming or something like this. So that's how the imaging detectors in the infrared came about. And then the adaptive optics came about because the military wanted to check out the details of spacecraft up there. Yeah. And so in the US, by getting that technology to come out of the military sector, the classified sector, was wonderful. And who did it? Towns. Because Towns actually was deeply involved in many of these connections between research and the government. And at the end of the Cold War.
For the Jasons, he was a...
That's right, exactly.
Jason's here.
Yeah. Yeah, he was the one to suggest that Jason be founded. And no, it's clear. I mean, I should say in Europe, there was a civilian type development, both of the adaptive optics, but also infrared detectors. Initially, that couldn't be on par with the US just because, the amount of money you have to have in order to develop a system like that initially is so high that the kind of money astronomers had in either US or Europe wasn't enough. But nowadays it's different actually, so that nowadays astronomers develop top technologies, detectors and so forth themselves. I'm mentioning this because Martin Harwood once wrote a very influential book where he basically, his thesis is that without the access to military technology, astronomy never would have gotten where it is now. And there's truth to that. It's actually truth to that, certainly in space.
Yeah, there's always been a partnership from Galileo, the first telescopes that he invented or he used. He tried to sell to the Venetian Senate to use for military spying on ships in the lagoons of Venice. So that was one of the first things he realized he could make money off of astronomy. And so, yeah, there's always been some connection between the military and now we see, basically the Hubble Space Telescope is kind of on a par with some of the best military spy satellites, except it looks in the opposite direction. And speaking of space, what would your project, the gravity group, what would be the evolution, and what could a spaceborne, where you don't even need adaptive optics, or are we going to be there with things like JWST, or are we going to be able to observe future follow-ups to not only the massive black hole in our galaxy, but maybe in others as well in the infrared?
Yeah, well, that's a very good question. I would say at first, most of us thought that the sky was the limit. And indeed, you would go ahead and build ever bigger telescopes in space. And you see, I've had the privilege to be associated with two major space projects as a PI institute, as well as being chair of various committees on the European side, ESA, the European Space Agency. And so initially, for very long wavelengths, infrared astronomy, far infrared astronomy, we all were thinking about an object in a telescope of substantial size. And in fact, the US thought they could launch a 30-meter telescope, 30 meters. Now, you have no rocket where this would fit in. Therefore, the idea was, you may recall these pictures of, astronauts, assembling such structures in near Earth orbit and building this, as it was called, the Large Deployable Reflector. Now that fell apart for the following reasons. Reason number one, we astronomers learned that near Earth orbits is no good, absolutely no good. And even if you had a telescope there, it would still be disturbed by the Earth because of its thermal influence, all the space junk up there, et cetera, et cetera. So we want, certainly in the infrared, but also now cosmic microwave background studies and so on, you want to get away from Earth as much as possible. And okay, so no astronauts, with a screwdriver. So you would then think about, like in the case of James Webb Telescope, structures which you can fold, and then when the launch is taking place, you basically unfold and so forth. But that's very risky, and we'll see. I really dearly hope when James Webb will be launched that it will actually unfold as prescribed. And so in Europe, we felt that this was just not possible. Unfortunately, because we had then a similar mission, which in the end got launched as a 3.5 meter telescope, but it started as a deployable 8 meter telescope, and we had hoped it would be that size. And in the end, the engineers in ESA said, no, it's too risky. Whether that's the right decision or not, I don't know. Certainly, historically, I would say the more cautious Europeans, as a result of their being more cautious, they went faster, actually. I mean, the James Webb has been on the books since the 90s, okay? And they still don't have it up there. And now let's go to interferometry. And here the story is quite similar. In principle, it's obvious what you have to do, right? I mean, you have to take launch, 4, say, 2.5 meter class telescope or something like this into space, and then, do magic to align them. That should be possible. I mean, that's how ELISA also will want to operate. The problem, again, is station keeping, technology, and then the cost. Certainly in Europe, we just had a review again of the ESA space mission led by Linda Taccone, and they looked at a space interferometer again, and in the end threw it out. And even in the US, I mean, the idea of a space interferometer was around one or two decadal reviews ago, right? The TPF, the Terrestrial Planet Finder, my God, I mean, that's what everyone would like to do. But it wasn't realized, too costly. And so I'm afraid there is a sort of a truth in Martin Howard's statement that there is sort of a limit. I call that sort of the region of death. It's like in the super collider, yeah? If a project becomes larger than something, and the James Webb is awfully close to that, then at least you have to be fearful of that your project gets dragged out for sheer incredible amounts of time, more than perhaps the lifetime of a single scientist. But it can't. If you go too far into this territory of death, it's just societies will not, or at least understandably, will hesitate.
That's right.
To spend that much money. So that's why I would say, I'm afraid, for now, it's gravity. And here I want to come back to Charlie Towns. And Towns wrote once a very nice piece for annual reviews of astronomy and astrophysics, one of these chapters on himself. Yeah. And he described what he had done in astronomy, and amongst you will find interferometry. Okay, now you said interferometry is 90 years old. That's absolutely correct for the radio astronomy side. But you go to the infrared, where you are much shorter wavelength. The atmosphere is shorter coherence time. And on top of it, typically you have larger bandwidth. All of it conspires to make the problem more difficult by the factor of 100,000 or so. And so what is a pretty obvious thing to do in the radio, and still pretty obvious in the millimeter, becomes absolutely, extremely difficult in the optical. Now, Towns did it used a trick at the time. He used 10 microns again, so a little longer. And he transformed the long wavelength, 10 micron radiation into the radio through mixing. Okay, so mixing with lasers. And so that made it possible for him to do a difframeter. In this wonderful little paper of his, he actually says, what I really want to do in the end is to look at the black hole with interferometry.
Wow.
So that's what we've now done. In fact, unfortunately, we succeeded only after he's passed away, but I knew about what we were doing. But now, just to tell you, I mean, the effort or the complexity in the end, the sensitivity, all of this, what we in the end had to realize was about, I would say, 100,000 times better than what Charlie had done. Yeah. So that's
about a plan to use the Keck, 2 telescopes of Keck to do interferometry, either in the optical or in the, sub-micron. And to my knowledge, it didn't produce anything. It was a vast technical challenge, and maybe it will, maybe it won't someday. But yeah, it's exponentially harder to do it for the reasons that you mentioned. And I want to take one other step, maybe laterally, and focus on these questions that you kind of are rare, Reinhard, because you have a commanding knowledge of the experimental side, of the practical side, but you also obviously understand the theoretical implications. A lot of my work in, as a teacher, as an experimental astrophysicist and communicator, is to tell people that there are other people, Sir Roger is wonderful, Stephen Hawking's wonderful, but these are theoreticians. And I almost feel like a good experimentalist should know the theory as well as a theorist, but maybe not create new theories. I mean, I think that's too much. But if you're just applying, the technology without understanding the theory, I don't think that's a fulfillment of what an experimentalist should do. And so I guess what I'm asking you is, what is your philosophy of a well-rounded scientist? Charlie was a paramount person like that in the tradition of Enrico Fermi, one of the last people that could do theory, that could do experiment, that understood the fundamental question. What is your philosophy? The students that you mentor, the postdocs, et cetera, what do you try to inculcate in them to have them fulfill their potential as a complete scientist?
Right. I mean, I would not have the audacity to say that I understand the theoretical work at the depth which is needed in the end to make reliable statements. Okay. So, for instance, if you want to investigate, the star cluster in the center and make a proposal how these stars would come about, that's sufficiently complicated, I would say, that I certainly wouldn't be able to do that. And so here's rule number one: is you have to have a team, and after all, that is what happens. It's not a single individual here; it's a substantial team, which in our case, of course, grew over time. Was initially largely based at MPE, but is now European. Okay, I mean, the interferometry is really involves at this point about 100 people. So that's clearly not done anymore, even at a pretty well endowed Max Planck Institute. But it's the range of people in a team, so that you can talk to people about various things. And Towns knew that as well. Now, of course, his mantra, I still know, was, the people at NASA are doing this, that, and the other thing. No, I don't want to do that. I think the best science is done only with a student.
Yeah.
Towns would insist on that philosophy. That's where I would not agree with him. I mean, the fact, we talked about interferometry. You can, in hindsight, you can, see his interferometry as an incredible amount of pioneering of a field, but you could also call it a failure, because that he wouldn't get to the galactic center type sensitivities was clear after a fairly short period of time. And so this, you have to bite the bullet sometimes. You have to realize, okay, if you want to get there with this type of technique to get that kind of resolution, you will have to go into a different domain of work. And that then includes larger teams, and that includes collaborations. Towns would like to collaborate with other teams. It was always, the fifth floor in Burge. I mean, that's how we lived up there. Everyone, up there was part of the gang. But but I mean, I think I am very proud that over time I managed to bring to fruition and create what I call my Champions League team. So we have people in Munich who are top people, world-class people by themselves. Could be top people anywhere, and the fact that they in the end chose to stay rather than become professor elsewhere. I mean, that happened too, but I'm extremely glad for that, because that's the kind of thing. Now, of course, another thing which I would say is important in addition to this sort of range of things, you have to write kind of hunting skill or smell. Okay, you have to sort of know what is and what isn't possible, and where, the time is ripe to get in. I mean, again, I could go with the interferometry and say, of course, I mean, I grew up as a radio astronomer. In my thesis as a student, I used VLT-a to look at water vapor masers and their motion. So I'm an interferometrist at heart. Still, it was clear until, about 15 years ago that interferometry in the infrared, forget it. Yeah. Not at the kind of sensitivity. But now that's very different. What we are looking at here is sort of the central few arc seconds in the upper left of the galactic center. The upper left is sort of the best you can do with a 10-meter class telescope in seeing limited conditions. So what do you see? You see some very bright, near dark stars. Okay, these objects are really very massive. Some of them are 100 solar mass Wolf-Rayet stars and other stars, very near the center. Now, the center is right in the middle. Yep. Okay? And so if you had radio eyes, then you would see in this very center this compact radio source Sagittarius star, which was sort of the first X marks the spot kind of situation. So the adaptive optics then improves this image from the top left to the top right by about a factor of 20 in resolution. So with a 10-meter telescope now and adaptive optics on under very good conditions, wow, now you can see individual stars very clearly. Some of the brighter ones, of course, you can see the artifacts of the adaptive optics not being perfect. You see this sort of ringing there. Yeah. And then now in the center, all of a sudden, there it is. That's J star. That's the black hole, which also radiates. Okay, and just on the top part of it, there's a little spot, the upper part of the small square. That's that star S2. So this image actually is from this year. So this star S2, which has been our key object to look at for these orbits, is already now sort of gone outside of the center. This year, okay? It was very near, in fact, more or less on these scales of the central object. But now the interferometry, so go here now from this upper right image to the lower right image, okay? And again, that's this little square which you see is now what you see as a big square on the bottom. Yeah. Okay, and whoops, what do you see? Not only one object, but heck, 1, 2, 3, 4, 5, 6, or whatever. Yeah, wow. And that, in fact, is what the breakthrough is. The breakthrough is the resolution, and therefore the precision of measuring things very accurately. But the other thing is also, of course, we can actually now, with this kind of interferometry, finally go deep. And so these fainter stars, which you see there, are fainter than what you can see in adaptive optics on the upper image, mainly because of confusion. It's not that, a single adaptive optics assisted telescope can go very, very deep. But in a crowded field like this, that's not the limit. The limit is really how you can distinguish. Yeah? And then you take several of these images over 3 months, and then you get the left, the bottom left. Okay, so red was in March, green is May, and blue is July. And wow, I mean, you look at that. I mean, there's very obviously one star which came extremely close, even closer than S2. Another one is sort of moving the other way, and there are a few more. Yeah, so it's that's really the key thing. And I would say the interferometry is a very serious contender now, in my view, for certain types of measurements one would like to do. One other application where it's been a breakthrough without our actually expecting it was exoplanet spectrum. So you wouldn't think that. I mean, if you think about these exoplanets, I mean, the problem is you have a planet, and then you have the much brighter central star. And the way usually this is dealt with is you basically mask the bright star, and then you look only at the planet. Well, with adaptive optics, that's fine, because then the star becomes relatively compact and you can actually see the planet. But the adaptive optics is not perfect, and the star is say 1 billion times, or certainly 1 million times brighter than the planet, and a little bit of this uncorrected light is then floating around near the planet and generates noise. So the noise is now not anymore instrumental, so to speak, but it's due to uncompensated light from the scattering from the star. Right. Yeah. And so the interferometry, on the other hand, doesn't do that, because the same effect in the adaptive optic systems on the individual telescopes which we're using also make not perfect correctors, but they're not correlated, and so the interferometer blends that out completely. So that's why all of a sudden currently the spectra which we're producing with gravity of exoplanets are the best in the world by a factor of 10.
Are there any applications of polarimetry? I know that in reflectometry, et cetera. How can that be used to enhance the scientific data?
Well, I mean, the galactic center, what happens is, you see, let's again look at the bottom left there. So this is what looks like a light blue object in the center. That's Sagittarius star. So if you take a time trace of that, then you would see it varying on typically timescales of 30 minutes or so, which, by the way, is the sort of orbital timescale of gas on the innermost stable orbit. Okay, so that's our interpretation. That's what you're seeing here. It's very, very hot, about 100 billion degrees, or 100 billion degrees gas, which is doing synchronous radiation. So it's polarized, typically 10 to 30%. So in fact, by using wave plates, we can analyze the polarization of the emission. And what we find is that the polarization is highly aligned. And so with that technology, we can actually study magnetic fields in the vicinity of the black hole. Extremely exciting. Extremely exciting, because one of the tenets in this field is that what you're seeing here, most people would say, is gas which has been accreted, although not like a quasar, but at very low levels. So there's a small amount of stuff falling into the galactic center. People would say an asteroid every 2 days or something like this, on this order. And that would explain the amount of radiation which we see. And then the magnetic field would be not in a disk, but in a sort of a donut of this hot gas. And if the gas is dense, well, then, as you know, the magnetic field is tied to the gas, and then it would be dragged along in this disk-like configuration and would have sort of a toroidal shape. When you look at what we're seeing from the variability, that's not the case. It's not toroidal. It's polaroidal. So, probably determined by the black hole. A similar thing has just been found by the EHT measurements in M87. So that really is a sort of a bit of a shock that the magnetic field structure is tied to the black hole itself rather than to the accretion zone. So that's the kind of stuff which you detect on the side, when you try
right. Yeah. It was an unintentional, serendipitous discovery. I think about, all the things that when I, the founder of this field, obviously Einstein in some sense, I had a conversation with Barry Barish last year, and actually inspired me to write a second book about called Think Like a Nobel Prize Winner. Hopefully you'll be in volume 2, but Barry was the inspiration for volume 1. And the reason was when he told me that he suffers from the imposter syndrome. And I said, oh yeah, I'm sure you did when you were at Berkeley as a kid and you were, around people like Lawrence or whatever. No, he's like, no. I feel the imposter syndrome now, even after winning the Nobel Prize, because when I got my Nobel Prize, I don't know if this happened to you, Reinhard, you're a very curious person, just like Barry is, but he looked through the logbook. I actually don't know if you've gotten the medal or whatever you've gotten, but he said when he accepted it in Sweden, he looked through the logbook to see who won it in the past, and he saw Feynman and Charlie and he saw Fermi and he saw Einstein. He's like, oh my God, I'm not worthy. He's too good and I'm not good enough. And I said, come on, Einstein was, he felt like he was an imposter compared to Isaac Newton. He actually wrote about Isaac Newton as being, the creator of all of Western civilization. And then I pointed out that Isaac Newton felt inadequate compared to Jesus Christ.
Look, Brian, it's very clear that amongst every group of people, and Nobel laureates are just another group of people. There's a range of excellence, if you like, and different. But then, I think I'm a little more cautious with the, how shall we say, the ultimate Einsteinian adoration. Because, if you look, Einstein did all of this, but it's not that he found the first solution, right?
That's what I was saying.
Structured and other things like the expanding universe you wouldn't believe, and he was on the wrong train there. And and certainly the whole issue of the philosophical discussion of the quantum theory and so forth, he was not always on the right side. So he had his failures too.
Yeah, I know. I always joke that it's too bad that he had that blunder, because he could have had a good career. But actually, what you're saying is exactly aligned with what I was going to ask you, which is that, given that Einstein didn't really believe in black holes, he called Lemaitre's idea atrocious. He thought that gravitational waves would never be detected. He thought that the quantum theory was unrealistic and should be based on reality and measurable principles. What aspect of your career might people look back on 100 years from now and say, oh well, Reinhard was too timid, he really didn't realize how powerful things could get? Is there anything like that, or do you feel like you're very optimistic about the future of your subfield and physics in general, that we are going to break to some ultimate law understanding of quantum gravity, or of the true nature of the information loss, or the nature of entropy in black holes, as a whole? What do you make of this?
Well, okay. Certainly I would say I'm a very much a pessimist. Most people feel that I'm sort of no, there's pessimism and pessimism. My father would always characterize this. My father was a physicist too, by the way. So he said, okay, well, there's two extreme types of people. There's pessimism, there's optimism, and there's happy and there's sad. The worst people are sad pessimists. Yeah, but actually, happy optimists are not much better. Okay. Yeah, and so I always hope that I'm a positive pessimist. But I mean, I think it's clear that we discussed this already, that we happen to be in astronomy right now in an absolutely incredible phase.
Yeah.
And this will not go on at this speed forever. Okay, that's one thing. The second thing is, depends on your taste. I use computers, of course I do, like we all do, but I'm not a hacker. And for my taste, if I were a new student now, I don't think I would go into astronomy, because I mean, I think it's just not my thing to only sit there and do MC and the rest of it.
No.
Just different people are differently. I use, if I want to test something, I would test things by basically looking at the project, a problem from different sides, and check out plausibility and so forth. And not only relying on, 100,000 MC. If the noise is not Gaussian, which it never is.
That's right.
What do you do, right? So I think that's clearly what in astronomy, what's coming next. Say, on the one hand, huge surveys where you can't really think about anything anymore, but you have to dump it into some, artificial intelligence thing. And then with artificial intelligence, I would say, okay, if you program the thing to recognize rats and dogs, and all of a sudden there's an elephant in the image, what does the artificial intelligence do? Okay, so sorry for inappropriate comment here, but so that's one side. The other side is that, as absolutely fascinating the exoplanet story is and will be in terms of, getting at the chemical composition of exoplanets and seeing all these different types and so on. I think that wouldn't excite me personally. It's just a personal preference. So I would go do something else instead. So it just, at least for me, I was lucky to be in the right place at the right time, and I think had the right mentors. I find that extremely important, and I find it a little sad that mentors have gotten lately, as a sort of a concept, into a bit of a bad reputation, because people feel, okay, well, maybe people are abusing the mentorship in some fashion. And certainly in a team, if you have only people who say, I want to be I, then, as you well know, that's not possible. You have to give and take a little bit, and it's all different types of people there.
When you mentioned, in a past interview, you consider yourself the son of two fathers, obviously Charlie Towns we talked about. Talk about your father, Ludvig. What would you like to tell him, about what you've discovered and what you're excited about, even pessimistic as you are?
Yeah, no, my father was, a super experimentalist. I'm a dwarf compared to my father. He would really do everything by himself. Even when he was already pretty bad shape in health-wise, he couldn't really move around anymore. He would go ahead and build little apparatus of all kinds, mostly electronic type apparatus, and then have young people come, and he would explain it to them. So he loved that enormously. And so my father was, as a physicist, was successful as a teacher, like hell. He's a solid state physicist, And I would say, his students and postdocs and so forth, he educated. There must have been probably 50 professors at German university. I think it's very, very successful at that. And everyone who heard his lectures was absolutely excited about that, including me. I, of course, inherited his superbly handwritten notes for lectures. And I used them here in Berkeley for quantum lecture, for quantum physics lectures and so forth. Really wonderfully done. I mean, in a very clear, very well spelled out, but understandable. Yeah, not hidden behind too much complexity and mathematics, but as obvious as you can make it. So it was very good. Now, initially when I was a boy, I had two things I was doing. I wanted to become an archaeologist, and then I did a lot of sports. My father didn't like that. That was not good. Okay, clearly. Now, the archaeology, it sort of evaporated after a little while because I realized that I would have to go to, I thought Greece and Egypt and so on was all done. And so where would I go? Well, somewhere in the jungle, and jungle has snakes, etc. No go.
You are a pessimist. Yeah. Vacation in Costa Rica.
And but in the sports, I really seriously, I tried to, go to the Olympics. I almost made it into the A team, but then my elbow, I did javelin throwing, so I was.
I didn't know that. What sport was that, Reinhard?
Track and field. So I was. I was. When I was 16 years old, I was Germany's best javelin thrower.
Wow.
But as I said, the javelin is a very tricky discipline because the centrifugal force, if you throw the thing more than say 70 meters at the tendons here, okay,
stress
is so high that if you're not perfect in technique, you basically rip out little bits and pieces of your tendons, which happened to me, and it happens to almost every javelin thrower. And then if you don't immediately get that fixed or not properly fixed, then you're out of business. And I did also the decathlon and pentathlon and these kind of things. But of course, once I studied physics, that I knew I had to make the choice.
So you did win a gold medal. Let's go.
Yeah. Okay. Yes. Yeah.
And then one question I had for you was your decision to move more permanently back to Germany. Was that more personal, or I've actually had Lord Martin Rees on my podcast earlier this year, and he was saying one of the models that's appealing is the Max Planck Institute model, where you're more decoupled from teaching and the responsibilities that say I have or you had when you were in Berkeley, and yes, you don't get to do the one-on-one with a student, or my friend and our friend Paul Richards, with his students, and he's been a great mentor to me, but you lose that. But on the other hand, you have more kind of I don't know, maybe more. There's more efficiency because you can only have postdocs and professor level people. So, was that part of the reason you moved back to Germany, or was that?
Well, okay. I mean, I think the situation in that sense was complicated. I love Berkeley. I really do. Yeah. I still do. That's why I'm here.
Yeah, that's right.
World was wonderful. Family liked California. In fact, my older daughter is here permanently in California. So all of this was wonderful. The weather was, double A plus. What else would you?
Better than
it was clear that. I mean, see, the Galactic Center is not the only thing I'm doing. I mean, I'm doing extragalactic cosmology of galaxies and so forth, and star formation and all of that, and molecular spectroscopy and all of that. And it was clear then that the kind of resources you would need for both building instruments, but also for doing things, would be definitely above the scale of sort of a single NSF grant. And you see, Townes was in a totally different regime. If you go back to his great times when he did the Maser at Columbia, the funding was very much like Max Planck. There was a colonel from the Air Force coming every year, he said, and there were at that time 2 Nobel laureates, Isidore Rabi and Cush. Yeah. He was the assistant professor, okay? In fact, Cush and Rabi tried to get Townes off the laser and Maser, right? And said, Charlie, you're a very good physicist, but this what you're doing there is not going to lead anywhere. We recommend you do some molecular beams. Okay, don't do this. This is gonna, you won't get tenure. But anyhow, so the colonel came every year and visited the labs. That's what Townes told you, and basically walked around, and they told them, showed them equipment they had and so forth. At the end of the day, he then said, "Well, that looks wonderful what you guys are doing. Well, I'll make sure the check is arriving next week." Yes, that was how things went at that time. And in fact, Townes for quite a while got this kind of a deal from the Navy. They gave him money directly without, But of course, when I was trying to do my thing here, like you and everyone else, how many proposals are you writing per year, and for ridiculous sums of money?
Yeah.
Okay. You use 2 weeks to be excellent for $5,000. Come on. And now here in Berkeley, there was a thing called Radio Astronomy Lab. So they, in fact, had state funding. Not anymore, by the way, which is the reason why the Radio Lab has ceased to exist. But all the wonderful discoveries, the millimeter interferometry, Jack Welch, and in fact Townes' discoveries with Jack Welch on detection of molecules, all were part of this sort of state funding thing where they had enough money to have a few senior people, postdocs, etc. And it was clear to me that it's that kind of funding was needed, but ever more impossible. And then came clearly the Reagan years where there was not all that much interest in this kind of thing. Okay, if you had connection to NASA, different story, but we didn't at the time. Okay, so that, and then on the other hand, I knew Max Planck because I had done my thesis at the Max Planck Institute. My father was the Max Planck director then, so I knew everything about the society, and I knew, well, okay, whilst Berkeley is great, probably Max Planck is a little better, and absolutely it was. I mean, that was blue skies or not, that was the right decision. Basically, this, what they call the long trust. So they basically, the process is pretty difficult and takes a long time, but then once you're hired, okay, there are visiting committees coming and checking on you, but really, it's a wonderful system. You don't have to write proposals unless you want to do more than sort of the standard funding of the Max Planck Group. Well, if you want to do that, then it's very difficult, but other than it's wonderful. I'm not sure, here comes the pessimist, that this system will, really be able to sustain the times, because it's too much, in a way, centered on the directors. So we are the senior staff. We have, as I said, the Champions League team is not recognized by the MPG. And that's, I don't understand it. And okay, now, of course, MPG and MPG is not the same thing. I mean, our institute, if you like, is an extreme institute in terms of cost of experiments, space work, and all of that. the typical institute, a typical Max Planck director has a group of maybe 10, 15 people. At the heyday of Herschel, we built almost 60. So, I mean, there are differences between institutes, but clearly we are not very well tuned to the situation that you have very senior, highly qualified senior scientists who have essentially no official recognition in society. Okay, who's this? Yeah.
Well, Reinhard, I want to finish up, if you have a couple more minutes left, with some questions that I ask all my guests that are so gracious with me as you have been today, and throughout the time that I've observed your career, and really been fascinated by the breadth and the depth that you engage in, from radio astronomy and work with ALMA and APEX, et cetera, and Atacama, to obviously the work that garnered you this Nobel Prize. So I want to first ask you a question that I asked kind of in the spirit of Richard Feynman, who said that the shortest sentence that summarizes the most information about the physical universe is what he called the atomic hypothesis, that everything's made of atoms spinning around. I want to ask you, what do you think is the most fascinating aspect of the physical universe that you've discovered in your life, that you'd most want to, say, engrave on a time capsule for other civilizations, maybe billions of years from now, when the people that live around Sagittarius star come to visit Earth? What would you tell them about what humanity has discovered as of 2021?
Well, I would say for sure the universe is beautiful. I mean, I think it's just, I always, my allegorical walk through the forest, where basically I say, doing astronomy in many ways is going into a new forest which you've never been in. And you look at all these beautiful trees and so forth, and wow, and they're so big, and there's this and there's that, and there is flowers there, red flowers and blue flowers and all of that. So they explore the universe and its beauty. And now comes the physics part. Then you discover, however, after a little while of studying, and you better be sure to study it well, that's what Towns would have said, then you would find that the blue flowers happen to be always on the left side of the road. Now that gives you a thought, why is that? Okay, why would that be? And then you develop an idea why that might be. Then you go ahead and test it, say, and you make more experiments and so forth. So that's my view. I mean, so there's the beauty part, awesome. And then the next thing is, of course, you then zoom into a few important physical questions and don't get. That's also important, of course. Don't get completely fascinated only by the complexity. I mean, then it becomes a hodgepodge of, undigested ideas. You have to get to this point where you're picking out the real gems of the wonderful universe.
That's delightful. Okay, so we went billions of years into the future with that question. Now we're going to go maybe 30, 40, 50 years back in the past. And it's the name of this podcast is Into the Impossible, because Sir Arthur C. Clarke, who's the namesake of the center that I co-direct at UC San Diego, he said the only way of determining the limits of the possible is to venture beyond them into the impossible. And I want to ask you, Reinhard, is there anything that seemed impossible to you as a 20-year-old, perhaps a 30-year-old, that because of your courage, you found that it was possible by only going outside your comfort zone? Is there anything that gave you the courage or advice to your former self that you would give to a young Reinhard, to go into the impossible? Any advice to your former self?
Yeah, well, okay. I mean, again, let me come back to the sports. I think that the sports for me was a uniquely preparatory. I didn't know that, but I mean, that's certainly, I would say, it's uniquely preparatory pre-exercise to do science, because you really sometimes have to bite you have to work extremely hard. You have to stay at it. You have to focus. And the focusing part is, I would say, something which I took from that, and that helped me to, get sufficiently deep. Some problems are just of a type where you have to look at it first. I mean, as I said, we like the forest. I mean, it's some people I see go into the forest, and then they exit again. Okay, but you have to first study. You have to really work hard to apply it, and then of course the other thing I said, you have to have a certain sense of smell where the blue flowers might be found, and how you check that out. I mean, and I guess I was lucky, and I had the right people with me.
That makes all the difference. Well, Reinhard Genzel, fellow colleague here in San Diego, or in California rather, at least for the time being, would love to get you down here in San Diego. If you can ever break yourself away from the winter time in Germany and don't want to visit your daughter, maybe you come down here and visit me in San Diego. I would love to see you in person again. We haven't been in person since that town symposium in 2005, and that's too long, although we've been together virtually now a couple of times. Reinhard, thank you so much for spending so much of your time with me and going into the impossible with my audience.
Okay, thank you.
Any sufficiently advanced technology is indistinguishable from magic.